Okay, so the next lecture in this unit is a big one, and the unit, of course, is called the wave nature of light. We're now going to get into light and analyze it. Is it a wave or is it a particle? And I know the title of the unit is the wave nature of light. That doesn't necessarily remove the idea that light is a particle. We're just talking about the wave nature of light. So I'm kind of leaving that open right now because we're going to study this. This was a big debate in science for quite some time. So we're going to go through what I call the story of light and our understanding of it. So the wave nature of light. This will be section 9.4 from your textbook. And we'll start just by talking about our understanding of light. So light carries energy with it. It's a form of energy. And we can tell this because when you're out in the sun, it feels warm. We don't know how light travels. I mean, we do, but from a regular person's perspective, how does light travel? That's something that typically people might not be able to answer. And how is energy from the light carried from the sun, for example, to our skin? So these are some questions that we had in science, and they were big questions that we had to have answered. So the nature of light was thought of actually, the earliest kind of time we see this brought up was with the Greeks. Plato had the opinion that light consisted of streamers or filaments that were emitted by the eye, and when those streamers came in contact with an object, sight was achieved. So basically your eye kind of shot out these streamers, and if your eye ended up catching on to something, then you could see it. Euclid agreed with him, and he argued, he said, how else can we explain that we do not see a needle on the floor until our eyes fall upon it? So if you're not looking at a needle on the floor, you can't know that it's there, but only when you look down at it, that's when you see it. This was kind of the idea, and it was, obviously you can probably think of some mistakes with this theory, but this held for a little bit of time. There were other Greeks that had different ideas, and Pythagoras, his followers were called the Pythagoreans, and you know him from his theorem, of course, a squared plus b squared equals c squared. But when he spoke about light, he imagined light as a fast stream or a stream of fast-moving particles. Another Greek, Empedocles, he taught that light traveled as a wave-like disturbance. So there was this early picture of light being a wave that Empedocles and his followers kind of followed. And then there was the idea that light was a particle, which the Pythagoreans followed. Of course, without a number of different devices at the time, it was hard to examine light and the nature of light. So it took until the 17th century until we started to have some more serious debate on the nature of light. And where we last left off, the Greeks left us with a particle theory and a wave theory. So, starting with the 17th century, we had the particle theory and the wave theory again. And the people who were in the particle camp were Isaac Newton, who was very well known at this point. He was also supported by a French mathematician and physicist who was known as Laplace. Laplace, when you get into university, you'll find out quite a bit of the mathematics that Laplace has given us, including the Laplace transform. Of course, that's well beyond the scope of any high school curriculum, but you'll see that he's actually quite significant in terms of his abilities as a mathematician as well as a physicist. So Laplace and Newton were quite renowned in their time. Newton, of course, being more renowned. And they held onto this particle theory. But on the other hand, we had proponents of the wave theory. And this was upheld by Christian Huygens of Holland. He was a mathematician and a physicist and an astronomer. He was also supported by Robert Hooke, who was the string person that we have Hooke's law come from. So he analyzed springs, but he was also in favor of this wave theory. Robert Hooke was the president of the Royal Society at the time, and he was a vigorous opponent of Newton. And if you really want to get into some of the personal and professional battles between Huygens and Newton, there's a good book by Bill Bryson called A Short History of Nearly Everything that goes into this quite well. But basically, Isaac Newton, he was in favor of the particle theory. Huygens and Hooke were in favor of the wave theory. Hooke had a very prestigious position at the time, so he had quite a bit of sway. But Isaac Newton was well known for, he kind of was starting a whole revolution in physics, and he was well known even by commoners, or rather, not commoners, but those who were not scientifically engaged people or academics. So his theory held weight as well based on his stature in the community. So both theories were plausible, and there was still a lot of time to debate these two. And it actually wasn't resolved in their time. So this debate between the followers of Newton and Huygens continued for over 300 years. And if you count from 17 to 300, that gets us to the 20th century, and we'll be talking about the earliest 20th century, which wasn't too long ago when some of these theories started to become more fleshed out. So the basic properties of light were understood at the time, and any theory had to be able to explain these things. They knew that light exhibited straight line propagation. They knew that light reflected and refracted. They knew that it dispersed, and they also knew, this was a big one, that light had the ability to travel undisturbed across millions of kilometers of space. So light traveled from the sun to the earth. And how did that happen? They didn't know, because we'll get into why that's such a big critical thing as well a bit later. So Isaac Newton's fascination with the ability of prisms to produce colors from white light, the dispersion, led to his development of the particle theory of light. So building on an earlier theory by Descartes, Newton proposed that light corpuscles, those little particles, with exceedingly small masses, travel in straight lines with a maximum velocity and therefore have kinetic energy. Newton's theory does not require a medium for light to travel in. Furthermore, he was able to explain the properties of reflection and refraction using his theory. But when it came to diffraction, then we started to see the shortcomings. So I'll just go through this reading a little bit and explain. So Newton looked at the dispersion effect, and he saw that light was broken up into a number of different component parts. And by doing this, he figured that light had a velocity that it travels at, which meant that it had a kinetic energy. And basically, by splitting the light up into its component sources, we were able to see the different wavelengths and the different ways that light can travel. So he imagined that if light was a particle, it didn't need a medium to travel through. So let's go back to space and say the big problem with a lot of these, or with the wave nature of light, was that we've talked about waves, and we know that waves can only travel in a medium because it's energy traveling by moving particles around. Well, if there are no particles and light is a wave, then, and there's no particles in space because space is a vacuum, then how is a wave moving through the vacuum of space? how is energy moving through space if there's no particles to move around? So Isaac Newton said that it's the wave, that it's not a wave because it's actually particles. Light is particles that are moving through space and coming to the Earth. Now, it says here that Newton wasn't actually entirely convinced of the correctness of his own particle theory of light. And he was actually surprised that some people approved of it so strongly, because he still had some doubts himself. But there wasn't any strong evidence for the wave theory at this time, and Newton was not willing to accept that light was a wave. And because of, again, his stature in the community, people ended up following Isaac Newton's theory more than Huygens or Hooke's wave theory of light. So we'll go into now Christian Huygens and Robert Hooke and how they define this this wave theory of light. So Hooke rejected the particle theory partly because two beams of light can pass through each other. So that was one of the things he said. If you point light at light, they pass through each other and they don't scatter. If you do that with particles, they would hit each other. However, Huygens encountered difficulty when he tried to explain rectilinear propagation, the straight line propagation, using the wave theory of light. So according to the wave theory, mechanical waves require a medium through which to move. So what medium was carrying the light energy? I've mentioned this a bit earlier, right? So the primary reason for Newton's theory, rejection of the theory, was that light, or rather waves, need particles in order to travel. And there were no particles in the vacuum of space. So Newton said, this can't be true because how does a wave travel without having particles to travel through? So it says on the side here, it says Huygens' principle states that all points on a wave front can be thought of as new sources of spherical waves. So that's another kind of thing to think about. I'm not sure how relevant that is, but that's okay. So next, it says Huygens' wave theory accurately explained the properties of light as strongly or even more strongly than Newton's theory in terms of reflection, refraction, partial refraction, diffraction, dispersion, and rectilinear propagation. At the time, however, there were no tests or observations that could eliminate either theory. So Newton's stature in the scientific community, gained for his many and varied contributions, including the laws of motion, resulted in his theory winning approval of other scientists for his less eloquent particle theory. So even Newton was kind of concerned about this because he thought, well, you know, I feel like it's better than the other guy's wave theory, but I'm surprised so many people just believe it just because I'm the one who put it forward. So let's look at both of these theories. We have Newton's theory and Huygens' theory. This is very good. This is good to copy down, as well as I would summarize everything in this lecture up to this point as well. So Newton's theory was the particle theory. Huygens' theory was the wave theory. Some of the main supporters of Newton's theory were Laplace. The main supporter of Huygens' theory was Robert Hooke. Reflection, refraction, and rectilinear propagation, reflection and refraction were both well explained by either theory. Rectilinear propagation was explained well by Newton's theory. But when it came to Huygens' theory, it was difficult to understand how we can have propagation of light, if it was a wave, in the vacuum of space where there are no particles. And Newton's theory, or rather Huygens' theory explained diffraction well, but Newton's theory didn't explain diffraction well, because how would these particles interact with each other if when we shoot beams of light at each other, they do not actually have any sort of diffraction. So, since no tests could eliminate either theory, and because of Newton's stature, the particle theory was the accepted theory of light from the 17th century and onward, until we started to have some new observations. So let's read this question here. It says, you shine a laser light through an open window. the window is kind of like a slit. The laser light does not diffract at all as it passes through the window. Instead, it travels in a straight line. What does your observation imply about the relative magnitude of the laser's wavelength and the width of the window? So, because we could shoot a laser at a window, and it basically looks like it just goes straight through, you can imagine that the window itself is a tiny slit that the light's passing through. But since we don't see any diffraction, that means that the lambda, the wavelength of the laser, is much less than the width or of the slit of the window. So lambda over W is less than 1, which is what we looked at in I think lecture 2. So diffraction doesn't occur if that's the case. And that happens because the wavelength is less than the width of the slit. So basically, that's why we're not seeing any diffraction if we shoot a laser through a window. So how must you change this experiment so that the electromagnetic radiation, which is what light is, does diffract through the window? So we have to change the wavelength of the laser, we can't change the wavelength of the laser light, because that's, if we do, we start changing what type of radiation we have. So we have to change the width of the window to make it basically a smaller slit. We have to make the window thinner, so it has to be actually thin enough that it is actually less than the wavelength of the laser light. Now, the wavelength of the laser light is in the order of hundreds of nanometers. And if we had a window that was that thin, it would probably break pretty easily. So that's something that's pretty difficult to do. Next here we have, it says Thomas Young showed that light passing through two parallel narrow slits produces a pattern of light and dark fringes. Does this support or contradict Newton's corpuscular theory of light? So we're going to get into this later, I think in the next lecture actually, but Thomas Young ends up doing this experiment later on, and he sees that if you pass light through some slits that are very thin, you can see an interference pattern. And it says the pattern of light and dark fringes contradicted Newton's corpuscular theory. So if light were like a particle, then the two bands of light would appear and no more. And we'll get into this a bit more in depth. But if light was a particle and it was passing through two slits, you could think of it as baseballs. If you're throwing baseballs at a wall that has two kind of openings, and you marked where the baseball hit on a wall behind that wall, they would only really be hitting outside where those slits would be. But if you pass a wave through something like that, you'll end up having an interference pattern. This is a big experiment, and this is just a small introduction to it. So don't copy anything down for your notes on this. I'm just trying to open it up for you so that we'll see where this discussion gets us in our future lectures.